In the previous episode, we explored Yokohama's future urban development, its TOD system, and the construction challenges of this project. From now on, we follow the actual construction journey of the Yokohama Landmark Tower, beginning at the bottom with the unseen foundation. Before erecting the frame, we must first complete the core that supports it or the frame. Foundation work is divided into 6 phases. Each stage builds upon the rest to form one cohesive robust system. This building wasn't erected on solid bedrock, but on coastal land. Soft ground posed one of the greatest challenges for a subwater structure. The sites were exhibited standard pedestrian test (SPT) and values ranging from 0 to 3, indicating a very loose state. Such conditions pose significant risk of liquefaction during earthquake and predicted long-term settlement exceeding 4 meters. According to a report by Mitsubishi Estate, a foam stone called the Kazusa layer was found about 50 meters below ground level. It can support up to 800 kilonewtons per square meter. A supporter building on soft ground improvement was not an option, but a necessity. The two methods employed were the sand drain method to promote drainage and the deep mixing method to increase ground strength. To stabilize the saturated compressible soil of the reclaimed land, vertical sand drains were inserted deep into the ground. These drains act like capillaries, rapidly channeling water away and accelerating consolidation, transforming subseed into buildable ground. In this project, sand drains with a diameter of 40 cm were installed at intervals of 20 meters. This arrangement effectively facilitated the drainage of water within the soil, significantly enhancing ground stability. In zones where drainage alone was not sufficient, the deep mixing method was employed. Cementitious binders comprising 20% cement, transforming clay-like layers into rigid columns. These columns with a diameter of 1.2 meters significantly increased the shear strength of the ground, enabling it to bear the immense weight of the superstructure. Design standards require slurry wells to extend at least 1.5 times the excavation depth. With 4 basement levels around 24 meters deep, the minimum was 40.5 meters. But to ensure stability and block groundwater, the wall had to reach the Kazusa layer at 50 meters. An extra depth was needed to prevent wall rotation, applying a safety factor of 1.4. The final depth was set at 70 meters, the deepest slurry wall ever constructed in Japan at the time. A custom-developed deep gripping rig was introduced to make it possible. After soil compaction was completed, the first permanent structure erected was the diaphragm wall, also known as the slurry wall. This wall was designed with a thickness of 1.2 meters and a depth of 70 meters, serving to block groundwater ingress, support earth during excavation, and ultimately function as the building's permanent underground exterior wall. Initially, continuous trenches were excavated deep into the ground to align where the underground wall would form. However, these trenches risk collapsing under their own weight and earth pressure. To stabilize the trench walls, high viscosity bentonite slurry was used to maintain pressure equilibrium. The slurry's viscosity was maintained at 25 seconds based on the Marsh funnel test, ensuring the stability of the trench walls. Subsequently, prefabricated rebar cages made of high-strength SD490 steel, yield strength of 490 MPa, were carefully rolled into place. These steel skeletons were arranged in a triple grid pattern to withstand horizontal earth pressure of up to 3,500 kilonewtons per square meter. Finally, concrete was poured slowly from bottom to top using the trimming method. During this process, the slurry was displayed upward and a continuous watertight wall was cast in place. The vertical deviation during construction was maintained within ±1/500, achieving high precision construction. The diaphragm wall serves 3 vital roles. It blocked groundwater, supported the earth during excavation, and remained as the permanent underground exterior wall of the building. To stabilize the excavation, H-beam struts were placed horizontally to resist earth pressure acting on the diaphragm wall. These struts formed a temporary bracing system that supported the vertical load from the surrounding soil. In addition, earth anchors were installed to provide passive resistance. By anchoring the wall to stable ground beyond the excavation line, the system gained greater rigidity and safety. Excavation proceeded one level at a time, and struts were installed after each stage. The excavation followed the star-shaped floor plan of the building, requiring precision at every turn. To prevent water intrusion during construction, a well-point dewatering system was deployed. This system lowered the groundwater table, allowing dry and safe working conditions at best. This image shows the actual construction schedule used during the project. Each process was intricately planned and tightly coordinated. A left foundation spreads rose through a wide mesh slab, but on soft ground that alone is not enough. A pile foundation transfers weight directly to deep bearing layer, but requires many piles and high construction cost. At the Yokohama Landmark Tower, engineers adopted a pile-left foundation, a hybrid solution. Here, the mat and piles work together to share the load, a system designed to safely reach the Kazusa layer, 50 meters below. After maintaining a safe offset from the slurry river, boreholes measuring 2.5 meters in diameter are precisely drilled 50 meters down to reach the Kazusa layer, an essential bearing stratum for transferring the tower structural load. Once drilling is complete, slime is removed using the airlift method. Then high-strength river cages are inserted. These cages are crucial in providing shear strength to each pile. Finally, concrete is poured from bottom to top using the trimming method. A total of 384 piles were formed this way, each designed to support up to 12,000 kN, approximately 1,200 tons, bearing 45% of the building's total load. The mat foundation was divided into a 5-meter base and a 6.5-meter upper slab. With a total thickness of 11.5 meters, it was unprecedented in Japanese architectural history. Drainage boards and mats were placed atop the ring concrete. These components efficiently discharged groundwater and infiltration water. The lower mat concrete was designed with a strength of 240 kg force per square centimeter, a volume of 24,800 cubic meters, and a height of 5 meters. On top of the ring concrete, rebar was arranged in a uniform grid pattern. This formed the structural basis for stress distribution and load transfer in the mat slab. Though the mat was divided into 10 segments, concrete was poured across all areas simultaneously. This approach minimized tensile stress at joints and ensured structural integrity. This continuous pour lasted 40 hours. Dozens of concrete mixers and pumps operated non-stop, working in seamless rotation. This process used the flexible hose method, delivering 7.5 cubic meters per minute to ensure optimal compaction and homogeneity. The cement was a low-heat mix of Portland cement, ground granulated blast furnace slag, and fly ash. This composition reduced hydration heat and prevented thermal cracking in mass concrete. Horizontal pipes and heat sensor cables were embedded in the concrete. Coolant and circulating water were used to regulate internal temperature and manage latent heat. After the lower mat, an upper slab was constructed to connect with the superstructure. It was designed with greater strength and a thickness of 6.5 meters. To connect the superstructure to the mat slab, Biocrete was used for the first time in the world. High fluidity concrete was injected into 600mm square steel pipes, preventing cracks that could occur during the pumping process. Once the foundation was complete, 64 fiber optic strain gauges were installed within the mat strap and a structural monitoring system was activated. It continuously tracked deformation, vibration, and waterproofing conditions in real time during the support structure construction, meeting ISO 18649 standards for dynamic vibration monitoring. Especially during seismic events, the system detected liquefaction and groundwater infiltration in real time. During the 1995 Kobe earthquake, magnitude 4 at the site, the maximum interstory drift was recorded at 1/850 radians, far safer than the design limit of 1/200 radians. The foundation system effectively suppressed these ground shifts, proving its seismic resilience. The Yokohama Landmark Tower stands 296 meters tall on sub-reclaimed land in a seismically active zone. Over the 10 years following completion, its total settlement was just 38 mm, 24% lower than the projected 50 mm. Such foundation performance wasn't just an engineering feat, it was the foundation of the city's resilience. The foundation was constructed in 6 phases, combining piles and mat slab into a unified structural system via the pile-left method. The mat slab was designed with separate allowable strengths for upper and lower parts, controlling latent heat and ensuring structural continuity with the superstructure were essential. The foundation work of the Yokohama Landmark Tower went beyond merely supporting a structure. It became a globally recognized benchmark for validating the theory of soil structure interaction (SSI) in practice, establishing a standard for foundation designs in defense of soil. In 2023, the Japanese Society of Civil Engineers named this project one of the top 10 construction technologies of the 20th century, bringing renewed recognition to the silent strengths buried deep beneath Yokohama. Now let us walk you through our study plan.